Yeah, so hello everyone. Thank you for joining us. My name is Wajid and I'm the Executive Director of the Maths Volunteers Foundation. I will be chairing today's session with support from Shah. Um, so normally we go straight to the speaker, but today I would like to say a few words as our talk is also being broadcast at the Department of Mathematics, University of Peshawar. I would like to thank Professor Muhammad Adil Khan for organizing this. To those joining our session for the first time, welcome and thank you for being with us. Yeah, although the seed of Maths Volunteer was planted in 2013 when we started pre-tuition in our village, Mashkhil, but the foundation has been active for the past few years in organizing talks and short courses, sharing open scholarships opportunities, guiding students through application process, as well as reviewing their documents. Of course, none of this would be possible without the help of our amazing and enthusiastic team, and I would like to thank all of them. Our mission is to support students in achieving their academic goals and maximizing their potential. We strive to break the barriers between mathematics and the younger generation. And one of the key programs is to introduce students to active and exciting areas of mathematics. So we usually ask our speaker to provide basic introduction to the field and maybe conclude with the current research topics or any open problems or future opportunities. Today, our speaker is Dr. Ahmed Ellithy, a postdoctoral fellow in the Department of Mathematics at Uppsala University, Sweden. Dr. Ellithy received his PhD from the University of Toronto in Canada, where his dissertation was focused on the botanic static extension conjecture. And his research interests include geometric analysis, general relativity, and differential geometry. Today, he will talk about general relativity, black holes, and the Hooke conjecture. So thank you very much, Ahmed, for your time and for accepting our invitation. Just to add, please put your questions in the chat, and I will read them out for Ahmed at the end. And you may also ask questions at the end, and I will unmute you. Ahmed, please begin when you are ready. So thank you.
Thank you. Thank you very much for the warm introduction. Hello, everyone. First, I want to say thank you to the organizers for inviting me to talk here. It's an honor to be here. So before I talk, I will be talking to you about general relativity, black holes, and the Hooke conjecture, which are very big topics, and there's a lot to say. Okay. So before I talk about the Hooke conjecture, I want to give a brief and informal kind of story, not very rigorous yet, a story of general relativity and black holes, just enough narrative so that the conjecture feels like it's the natural next question and not just a random slogan. Then we're going to be a bit more precise and a bit more rigorous later. So first, in 1915, a long time ago, Einstein revolutionized physics by proposing that gravity is a space-time geometry governed by equations that we now call Einstein's field equations. Essentially, he proposed that we abandon the fundamentals of Newton's theory of gravity and Newton's theory of space-time and reinterpret gravity not as a force between masses, but instead as the geometry of space-time itself, and more specifically, the curvature of space-time. So he's completely reinterpreting gravity and space-time. This is, of course, for now very vague, and we'll be a bit more precise later. He specifically proposed that the object that encodes the geometry of space-time, which is called the metric, and I will talk to you later about that, the object that encodes the geometry must be related to the matter distribution according to some equation. And the equation is what we call Einstein's equation, Einstein's field equations, that you will see a bit later on. Then Okay, good. Then not that long after, just very quickly, another scientist, Schwarzschild, finds an exact solution of Einstein's field equations that specifically describes the vacuum exterior of a spherically symmetric body of mass m. So generally speaking, Einstein's field equations are very, very difficult to solve. They are specifically partial differential equations where the unknown is the geometry. And they are difficult to solve, but if you impose conditions on the space-time, reasonable conditions, like for example, spherical symmetry, or that the mass is spherical and there's nothing outside, there's vacuum outside, and maybe possibly other reasonable constraints, other reasonable conditions, then Einstein's equations can simplify significantly, and they can actually become, and after certain assumptions, they can become just a coupled system of ODEs, ordinary differential equations, which can be solved explicitly, and you find an explicit solution of Einstein's equations. And that is exactly what Schwarzschild does. And that solution is what we call the Schwarzschild solution. And again, it describes it describes a universe where you have one star, one spherically symmetric star, and nothing outside. And it's a very good model of our space-time, of our solar system specifically. So if we take the sun as our star, and suppose it's vacuum outside, so suppose that the other planets are of negligible mass and don't really affect gravity. It's a big assumption, of course, but if we assume that, then the Schwarzschild solution gives us a model of our solar system, and in fact, it's even more accurate than the previous models before Einstein. It predicts things that even Newton's theory of gravity and Newton's theory of space-time did not predict. So just the simplest solution of Einstein's equation ends up being revolutionary. Next, a bit later, people were studying this solution specifically, and they found something weird happening. So there's a critical radius. So the same solution, that's Schwarzschild solution, has a special radius, r equal 2m. If the radius of the star is equal to 2 times the mass with respect to certain geometric units, then the geometry predicts something weird. In particular, if you shine light rays on the surface of the planet at r equal to m, the light rays will be trapped on the surface of the planet. The light rays cannot escape. And if r is less than 2m, then not only they get trapped, but they start moving towards the center of that region. So in other words, there's nothing that can escape. Not even light can escape the region r equal or r less than 2m. So this was something that one did not expect, and the people first thought that, oh, this is just non-physical, so possibly Schwarzschild solution is not correct, or Einstein's theory is probably not correct if it's predicting some crazy things like this. But people started accepting it, and we call this a black hole. And this is actually how black holes were discovered. They were discovered mathematically first, before they were discovered physically. I mean, much later on, they were discovered physically through experiments, and the first picture of a black hole was obtained actually not that long ago. But it was discovered mathematically first in the solution, Schwarzschild solution. So we call r equal to m an event horizon, and inside we call this region a black hole. Now, in our solar system, the sun, its radius is much bigger than 2 times the mass. So we are far from that happening in our own solar system. But in a sense, if r gets smaller, if you kind of compress the mass in a small enough volume, then the geometry starts predicting weird things. Okay. Then much later on, in 1959 to 1962, the initial value formulation of general relativity was discovered. So So let me first explain that the mathematicians have been studying Einstein's equations for very long in an attempt to understand its solutions. Of course, this is very important because if we accept Einstein's theory, then our spacetime satisfies Einstein's field equations. So it is of great interest to understand the properties of those solutions, how do they behave, and so on. And an incredible revelation happened in 1959 to 1962. In particular, mathematicians were able to uh, they were able to pose Einstein's equations as an initial value problem, which means that if you have a time slice, so consider this as a time slice, just a slice of time in the space-time. If you have certain information in that time slice, if you know some certain things on that time slice, then you can extend uniquely. Then it extends uniquely to the full space-time. Then you know how the space-time evolves. You know the rest of the geometry of space-time. So given certain information at just t equals 0, you know the rest of space-time via Einstein's equations. And more rigorously, mathematicians discovered that under a certain gauge, Einstein's equations become basically a wave equation, PD, a wave equation on the components of the metric. And so if you have seen wave equations before, you're familiar with the fact that if you have initial conditions, if you have the induced geometry on initially, and you have the normal derivative or time derivative of the geometry initially, then that just gives you the space-time evolution. So this is the initial value formulation of GR, which was changed a lot. Now a bit later on, it was discovered that black holes are not just special cases appearing in exact solutions like Schwarzschild solutions. It ended up being something that is actually much more general, and they appear in broad families of solutions. And in fact, one can potentially predict when they will first form from the geometry of a single time slice. That is just due to the initial value formulation of GR. So you know that if you have information on a single time slice, you know the future and the past. So in particular, technically, you can, theoretically, you can read that some certain things in this time slice and see if there is going to be a black hole forming in the future or not. So that is the guiding question for this talk. The question is, how do we know if black holes will form? So can we read off the black hole formation somehow from the initial time slice? Specifically, can we compare something like the size of the matter with the mass of the matter and have some kind of condition written in this way, just on a time slice that can predict black holes? And that is what the physicist Kip Thorne thought of. And he came up with Kip Thorne is a physicist, came up with the Hoop conjecture, and he came up with a slightly more precise prediction or answer to this question. Okay, so the question is, when do black holes form? So a long time ago, maybe sorry if this is not clear. This is when do black holes form. So for a very long time, people have believed, since the discovery of black holes, people have believed this very vague sentence. If enough mass and energy is squeezed into a small enough region, then gravitational collapse will become unavoidable, inevitable, and a black hole will form. That has been believed for a long time, and the Schwarzschild solution is a specific example of that. If R is small enough that it becomes 2m or smaller, then gravitational collapse happens. Here I have a picture, describing the star. In a sense, you have a large collection of dust and gas. That's what stars are, and they are being compressed by gravity. And eventually, at some point, when the radius of the star gets small enough, then gravitational collapse becomes inevitable. So this is something that we just vaguely believe. However, it is very difficult to try to make this precise. Specifically, we don't know what small enough region rigorously means. In fact, we don't even know what mass and energy rigorously means. It has been an open problem for a very long time, and is still open to try to formalize this rigorously. So the question is, what does small enough mean? So here I'm gonna try to describe the thoughts of Kip Thorne and how he came up with his hoop conjecture. So what does small enough mean? So it can mean volume, small volume. So let's suppose you have. So the question here is which measure controls black hole formation? Suppose you have a blob of mass. Um, and so what does small enough mean in this sentence? So could it be just that the volume is very, very, very small? Or could it be that the radius is small? So some notion of distance from the center. Or could it be that the circumference is small? And by that I mean consider a hoop of a certain circumference, and you want to ask if you can pass the matter through that hoop. So one thing that you would naturally think of is that you would think that all these three things are pretty much the same thing. They are connected, and indeed they are in Euclidean geometry. If you control one of them, you control the others. So of course in Euclidean geometry, we are not really stuck in this step. They are all equivalent. If you know the radius, then you know the volume, and you know the circumference in particular. But generally speaking, in more general geometries that are not Euclidean, especially under the influence of gravity, those three things are decoupled. They are not the same thing anymore. They do not imply each other. If you have one of them, it does not tell you the others. So in more abstract and more arbitrary geometries, it is definitely more complicated. And I have a picture that tries to explain this. So this is the standard, like the so this is like the classic embedding style visualization. So it's not the whole space-time. This is just how to picture a single time slice in the space-time. And you're imagining how the single spatial slice is stretched. How can it be stretched by gravity? So with a black hole, it's stretched a lot. And in flat space, if there's vacuum everywhere and there's no curvature at all, then there's no stretching at all. This is just Euclidean. If there's a star, then the time slice is stretched a little bit. Okay, so here's the thing with volume. The volume inside can be very, very, very huge with a black hole, but here it can be very, very much smaller. So you could have a situation where you have a very small region, but the volume in the interior is very large. And same thing with the radius. Because of the stretching, the radius could be very, very large. So this gives us a hint that the answer is not volume and is not radius. And this is what Kip Thorne kind of figured out. He figured out that the circumference is the key quantity that determines when is a region small enough. The good thing about circumference is that if you have a hoop with a certain circumference, it does not really see, in whichever situation, the flat space or star or black hole, it does not really see the geometry of the interior. So an observer can technically measure this without needing to understand the interior of this hoop. And we do not want to, because we don't quite understand what it will be. It could be very large. So that is the beginning of Kip Thorne's idea that circumference is the key quantity that can make this statement a bit more precise. And he came up with this hoop conjecture. And to try to figure out if this is really correct or not, he made a thought experiment. If I take matter and squeeze it radially into a very thin cylinder while leaving it very extended along its length, the question is, do I force a horizon, and this event horizon that I was telling you about later, or do I force a black hole? So what we mean here is that suppose you have two types of matter, one that is a spherical blob kind of matter, and other that is just a cylinder. And here the spherical blob can be made very small in a sense that no matter what hoop you have, if the hoop is small enough, it will pass through the entire matter ball. But here for the cylinder, you're compressing the matter only in 2 dimensions, only here, but you're not compressing it in the third spatial dimension. So a small hoop can go through the matter in 2 dimensions, but you will need a very, very large hoop to go through the matter in the third spatial dimension. And he realized by studying Einstein's equations, he came up with actually specific explicit solutions in which you have matter compressed in this way in an infinitely thin cylinder and still no horizon forms. and he still finds that no horizon forms in that spacetime. Uh, in a sense, not proving, but suggesting that indeed, to get a black hole formation, for a black hole to form, you need the circumference to be small in every direction. You need to compress the matter in every possible direction. So, and that is Throne's takeaway here. Of course, there's a lot of math involved here, but he came up with an explicit solution of Einstein's equations that have this, and he showed that there are no horizons. So for an infinitely long cylinder, squeezing the radius r goes to 0 still does not produce a horizon, in the same way that spherical collapse does. So the intuition is that gravity, in a sense, is spread out in this way. So it never gets compact in all directions. So the idea is that to form a black hole, you must compress matter in all three spatial directions, supporting the idea that that for a black hole to form, we need to measure the circumference. The circumference needs to be small enough. The circumference of the required hoop to pass through the matter needs to be small enough so that a black hole forms, as opposed to volume or radius. Because here the volume can be very small or very big. The radius could be very small also, but that doesn't lead to a black hole. So we came up with his conjecture, which is a bit more precise than the naive sentence before. A horizon forms if and only if, he gives a necessary and sufficient condition, if and only if a mass m is compacted so that a hoop of circumference c can be placed around it in every direction. So you want to compress every spatial direction, with c small enough in the sense that it's less than or equal to 4 pi m, where m is the mass of the star. Here I'm using certain units that makes this equation simpler, easy. The constant 4 pi here doesn't come from nowhere. It comes from the fact that we want this to agree with the Schwarzschild solution. So with c equal 2 pi r, this at the end gives us r less than or equal to 2m. And this is, 2m. And this is exactly what happens in the Schwarzschild solution. And this is where the 4 pi comes from. So that is Thorne's hoop conjecture. And that has been open for a very, very long time. And it's still open. And the main obstacle in trying to prove this conjecture is to even state it in a rigorous way. We still don't quite have an accepted definition of mass, and we still don't have an accepted definition of circumference. So the main difficulty in trying to prove this is to actually come up with a precise formulation in which we can actually think, is it true or false? However, the good news is that not too long ago, less than 20 years ago, it has been resolved under the assumption that the space-time is spherically symmetric. Less than 20 years ago, there is a natural choice of definition of mass and a natural choice of definition of circumference that makes this statement true. And I will give a sketch of the proof at the end. But the general conjecture is still definitely open. Okay, so now we have been talking vaguely so far, without any definitions, or we have not been very precise. So now let's be a bit more rigorous. We're not going to be too rigorous. It takes a long time to understand the language of GR, but we will be a bit more rigorous to understand, what space-time means, what black hole means, what any of these words means, mass, circumference, and all that. Okay, so let's start with, okay, well, maybe this should be there, maybe. Okay, let's start with this. Let's start with the beginning. It's a slightly more rigorous summary of general relativity. So GR can be summarized in this single sentence. A space-time is a four-dimensional, something called manifold in quotations, equipped with something called Lorentzian metric, satisfying something called Einstein's equations. And I want to give you a bit of an idea of what each of those words mean. So more specifically, the space-time is just defined to be the collection of all events that occurred in the universe. That forms a four-dimensional manifold. A manifold is a generalization of R4, of a four-dimensional Euclidean space. We cannot impose any restriction on the topology of the space-time, so we cannot really say that M is R4, but it is four-dimensional. And manifold is the notion that is a bit more general than the special case R4. So if any event happens, let's say a flash of light, that's an event. Let's say a flash of light happens at some point in time. That's an event. That's the point in our set, in our space-time. If we have an observer, so an observer is someone that is measuring distances and time relative to him or her. If we have an observer, then each point P can be assigned four numbers, T, X, Y, Z. T is the time the event happened with respect to that observer, and X, Y, Z is the position in which the event happened with respect to that observer. So this is all with respect to that observer. So here I'm just drawing a vague picture of space-time. I cannot draw four dimensions, so we are collapsing the three-dimensional space in R3, and we have the time direction here. But remember that this is the cross-section here. This is not a plane, this is R3. But I will always collapse one of the spatial dimensions so that we can draw it and not suffer. Okay. So essentially, for the mathematicians, by observer, I mean coordinate system. In physics, we call it an observer, but in math, we call it a coordinate system. A coordinate system is just a way to assign each point on our manifold four numbers. And those four numbers are definitely dependent on the coordinate system, i.e. Physically dependent on the observer. Okay, so now let's talk about geometry. What does geometry mean? So M is equipped, so the manifold is equipped with this Lorentzian metric. What does metric mean? This is not like a metric in the sense of a metric space in points at topology. It's a different kind of metric, but it has the same name, unfortunately. So a metric is what gives a geometric structure to the manifold. And it is more rigorously, it's for every point, it's a choice of an inner product on the tangent space of the space-time at that point. So if you have a point, you can consider the tangent space, which is all possible vectors coming away from that point. And that's a vector space, that defines a vector space, a four-dimensional vector space. And on that vector space, you can define an inner product. And you do this for every point. You do this for every point on space-time. You get G. For each point in space-time, you make a choice of an inner product. An inner product is something, of course, you have possibly seen this before. An inner product is something that takes two vectors and gives a number and is linear with respect to each component. The Euclidean dot product is a specific example of an inner product. You have seen this before in high school or so. So we're doing this at every point. Of course, in a smooth way. This can be made more rigorous, but we'll move on. So what do I mean by Lorentzian? By Lorentzian signature, I mean that let's say if you fix an observer, i.e. you fix a coordinate system, then at that point you can have the coordinate basis vectors, the vector in the t hat direction, the vector in the x hat direction, the vector in the y hat direction, and the vector in the z hat direction. It's just a coordinate basis. It's a basis with respect to this observer at the point. And it is always true that the inner product of t hat with itself is negative and the rest are positive. So in particular, this inner product is not positive definite. It's not like the Euclidean inner product. So you can indeed get vectors that their inner product is negative. So it is not a positive definite inner product. Okay, so a metric G gives M a geometric structure. Why is this choice of inner product really related? How is this related to geometry at all? In fact, it is precisely geometry. By geometry, we mean a metric, at least in this context. By geometry, we mean a metric. In fact, one defines a geometric notion as a notion that depends on the metric. So really, once you have once you have a metric, then you can talk about geometry. You can do geometric things. You can define geometric notions. And I'll give you some examples. So with a metric, we can define length of vectors. If you have a particular vector, you can compute its length. It's the square root of the inner product. I have to put absolute value because it could be negative. But you see that the length of a vector is indeed a geometric notion. It depends on the inner product. Another example is the angles between vectors. That is another geometric notion. If you have two vectors, you can talk about its angle, and you can compute its angle this way: the inner product divided by the length, the product of the length. If this is positive, we can say it's cosine of the angle. If this is negative, we use the hyperbolic angle, cosine, sinh, and all that stuff. But either way, angles are an example of a geometric notion, and indeed they depend on the metric, on the choice of inner product. Another example is the length of a curve. If you have a curve, the length of a curve is absolutely, definitely a geometric notion. And indeed, it depends on the metric, because just from the formula, you can see it's the integral of the square root of the norm of the velocity vector of the curve. So if you have a curve at every point, you can consider the velocity vector, and you can calculate the norm of that velocity vector, and that is obviously depends on the inner product. Integrating that over the curve gives you the length of the curve. So the length of the curve is a geometric notion, of course. It depends on the metric. Another example is the notion of geodesics. You might have seen that before, or maybe not. A curve is, in a sense, is the straightest possible curve between 2 points on a manifold. So a curve joining P and Q is a geodesic if this is very vague, but it's really defined more precisely than this. If the length of the curve is the infimum of the length of over all possible curves joining P and Q. This is true assuming P and Q is small and close enough, but that is vaguely speaking what a geodesic is, and indeed it is a geometric notion. So the straightest possible curve is a geometric notion. Finally, not finally, but next is the area of a surface. It's computed this way. You can compute the inner product on the subspace spanning the surface in your spacetime. And this double integral is the definition of the area, and indeed it is a geometric notion. It depends on the inner product. And finally, notions like the gradient and divergence and curl, you might have seen them before. They're actually geometric notions. You might have seen them in Euclidean geometry written in a certain way, and you might not have thought that they are actually geometric, but they are indeed geometric. They do depend on the inner product. What you probably have seen, if you have seen the gradient and divergence and curl, you probably have seen those notions in Euclidean geometry in some coordinates, in the Cartesian coordinates x, y, z, and they take a very nice special form in Cartesian coordinates. But these can be generalized to general manifolds equipped with a geometric structure. Okay. Now, next is, okay, so a big difference between Euclidean geometry and Lorentzian geometry is that we can have negative lengths. So as a consequence, we have a natural trichotomy of vectors. Trichotomy of vectors in Lorentzian manifolds. If you have a vector tangent to the space-time at a point P, we say that V is time-like. If its inner product is negative, it's space-like. If its inner product is positive, it's null. If it's zero, we can draw again space-time here. Again, I'm collapsing one spatial direction. There's a reason why we call it these words, and I'll explain why. We can consider all possible vectors coming from this point, a fixed point P, all possible vectors that are null, and this defines a cone. Remember that this is a three-dimensional cone. Again, I'm collapsing a spatial dimension, so this is a three-dimensional cone. In particular, if you take a cross-section, the cross-section is not a circle, the cross-section is a sphere. So let's just remember that for later. Again, I'm just drawing it as a two-dimensional cone, but it is a three-dimensional cone. So all such vectors define a cone. And if a vector is inside the cone, it's time-like. If it's outside the cone, it's space-like. And that can be, proven very easily with standard linear algebra. We also call this time-like vector in the future directed, and this is the past directed. We can also have these notions in curves. So we can also have a notion of time-like curve and space-like curve and null-like curve. So if you have a curve, the curve is time-like if at every point the velocity vector is time-like. And the curve is space-like if at every point the velocity vector is space-like. And similarly for null. The word lines of particles, so if there's a curve that describes the path of a particle or light, then it will be described by a time-like or null curve. Because if you're going in the null direction, then you're going at the speed of light. If you're time-like, you're moving at a slower speed. If you're space-like, you're moving at a faster speed faster than the speed of light. So word lines of particles will be traveling through time-like curves, and word lines of light will be traveling through null curves. And space-like curves don't really have any physical meaning, as far as I know. Okay. We can also talk about not just the future of one point. We can talk about the future of any region. So take a region S in space-time. Let's say a three-dimensional region. Again, I'm drawing it as a disk, but think of this as a three-dimensional object. The causal future J plus of S is defined to be the set of all points in M that can be connected with a point in S through a future directed time-like or null curve. So a point, let's say this one, is in the future of S if it can be connected to a point in S via a time-like or null curve. So in particular, physically speaking, such points are points that can be impacted by events happening in S. So if you have a point outside here, there is no time-like curve joining this point with S. Uh, and so this point, this event cannot be influenced or impacted by any event in S. So indeed, we call this the future of S, and we can also define the past of S. If S is instead a two-dimensional region, so just the sphere, which I'm drawing as a circle, then it's a bit more complicated to compute its future, but you will see that the future will be precisely what's in between those two cones. Notice that any point here, there is no time-like curve that that connects to a point in my surface S. So this part, the inside of this cone here, will not actually be in the future. The cause of future J plus of S will just be this. But if I include the region inside, then of course this becomes also a part of the future. So this will be important because this will be called outgoing cone, and this will be called ingoing cone a bit later on. Okay. So now I want to describe, vaguely speaking, what general Einstein's theory of gravity really proposes, or what Einstein's field equations say. So general relativity is essentially a theory of gravity that replaces the old Newtonian theory of gravity. So let's first review what Newton believed. Let's review Newton's theory of gravity. So any theory of gravity needs to explain two things. First, how does matter create gravity? How does matter create a gravitational field? And second, how does a gravitational field influence the motion of matter? So there are two questions. They affect each other. Matter produces gravity, and gravity affects matter. So if you have a theory, if you have a mathematical theory of gravity, it needs to answer both those questions. So how does Newton answer both those questions? So the first question is, matter creates how does matter create gravity? It creates a gravitational field via the Poisson equation. That is Newton's theory of gravity. Phi here is called the gravitational potential. It's a function, and its gradient is called the gravitational field. It's essentially the gravitational field is essentially the force of gravity on a particle of unit mass. That is what gravitational field really means. And so Newton asserts proposes that gravity is a force, and the force, or the gravitational field, is obeys the Poisson equation. Laplace phi equal 4 pi g rho. Rho here is the matter energy density function. So if you have matter density, if you have matter, then it affects the Laplacian of phi, and so it will affect phi. So that's how Newton suggested that matter creates gravity. If you have a matter distribution, then you have a potential that must satisfy this equation. The next question is, if you have gravity, how does it influence the motion of particles? That is much easier to answer in Newton theory. Well, he interprets gravity as a force. So if you have a force, Newton's second law of motion says that if there's a force acting on a particle, then the force is related to the acceleration of the particle via this equation. So the force is proportional to the acceleration with the proportionality constant mi. That's called the inertial mass. The inertial mass is a number associated to the object that we are studying, that is moving according to gravity. It is precisely the force required to move that said object at an acceleration of 1 centimeter per second squared, or 1 meter per second squared, or whatever units you choose. So that is what the inertial mass is. And he solves this equation. Oops. He solves this equation under the assumption that you have a point mass, and he finds that the force of gravity, he finds that Laplace phi is equal to this. mg here is the gravitational mass. M here is the gravitational mass of the star that is creating the gravity, or the point mass, and small mg is the gravitational mass of the object. So this is called the gravitational mass. And it turns out, after a lot of experiments, it turns out that these two things are actually exactly the same thing. That is called the equivalence principle, and it is one of the reasons why Einstein decided to abandon Newton's theory, because believe it or not, the fact that mi and mg are equal actually in some way contradicts this entire thing, this theory of gravity. But I won't go into these details for now. But that is Newton's theory of gravity, and so Einstein proposes that that is all nonsense. Let's repeat again from the beginning. If he comes up with a theory of gravity, he needs to answer two questions. He needs to answer how does matter create gravity, and how does gravity influence particles. First, how does matter create gravity? So he proposes that gravity is not a force, but instead it's the curvature of space-time. And he wants to relate the curvature of space-time, which he interprets as gravity, he wants to relate it to the matter density just in the same way that Newton does. Newton relates the gravity with the matter density in this equation. Einstein threw this away, and then he gives this analog. He relates the curvature of space-time. This is called the Ricci curvature of the space-time, and this r is a function. It's called the scalar. It's the scalar curvature, and g here is the metric that you Lorentzian metric that you have seen before. So the left side is something that only depends on the geometry. These notions of curvature are basically, it's in a sense second derivatives of the metric components, just like you would expect a notion of curvature to be second derivatives of the metric components. And the right side here is called the stress energy momentum tensor. It is something much more general than rho, the matter density, and it measures in a more complete way the matter distribution. So I won't go too much into details, but it's the analog of this for Einstein, and this is the analog of this. The second question that Einstein needs to answer is how does gravity influence the motion of particles? That also turns out to be the easier question. So he doesn't use F equal ma because he is not looking at gravity as a force. Instead, he's looking at the space-time as curved, and anything that is going along, any particle that is moving under the influence of gravity is not moving under the influence of a force. It's moving under the influence of curvature. And so the curve that describes the path of a particle under the influence of gravity is just the geodesic equation. As in, it's the equation that describes the fastest possible curve or the straightest possible curve on a manifold. So in this case, it might not be a straight line. If this is called the Christoffel symbols, if they are zero, if the space is flat, then you just get x double prime is equal to 0, which gives you just a line. So that is how Einstein proposes that gravity influences the motion of particles via the geodesic equation. X mu of t here is just parametrizing the components of the points in the curve. So at time t, x0 is the time, x1 is the position, x2 and x3 are also the position. Okay. Next, now let's try to understand more now what a black hole is and what a horizon is and how can we define it in general, outside the special Schwarzschild solution. So we're moving to a crucial geometric object, geometric concept that will help us explain this. This is called the outgoing and ingoing expansion. So suppose you have a surface S, and again, you know that the future of S is between those two cones. The boundary of this is two cones, C and the C line C. You can think of it in the following way. At every point in S, there will be exactly two vectors that are linearly independent that are null and orthogonal to S. There will be exactly two. Remember, we are in 4 dimensions. So there will be exactly two. One of them will span the outgoing cone, and the other will span the ingoing cone. So that's what's going on. So you have the outgoing cone and the ingoing cone. So here's something that we can measure. We can take, let's say, light rays, and so we can either shine the light outward, or we can shine the light inward towards the center of our sphere. If we shine the light outward, then after a bit of time, after let's say 0.001 seconds, after an instant of time, we can take the cross section, and it will be another sphere, maybe a bit modified sphere, and we can compute the area of the sphere. We can compute the area of the sphere at epsilon time. And then we can compute how does this area increase or does the area decrease. And the expansion is defined as the rate of change of the area of this cross-sectional area as we go in the outgoing direction. That is how the outgoing expansion is defined. It's very vaguely speaking is defined like this. And similarly we do the same thing for the ingoing expansion. We also define it as the rate of change of the cross-sectional area. Now, so you can think of it like this. So it's actually basically a divergence. If it's positive, if theta plus is positive, then that means the light rays are spreading out. The cross-section area is increasing. But if theta is 0, then the light front is instantaneously neither expanding nor contracting in a sense. It's like marginal. And if theta is negative, then it's converging, like for example here. The light rays are converging. So in flat space, in flat Minkowski space, if we take just this as the flat surface, theta plus can be computed to be 2 over r, where r is the radius of the sphere, and theta minus can be computed as minus 2 over r. And indeed, theta plus is positive and theta minus is negative. It's kind of, that's what's normal. That's what you would expect. But that will not always happen in an arbitrary geometry. If you have enough gravity, things can change. Before we go into this, there's an important equation, a geometry equation, together with Einstein equations that implies an equation on the rate of change of the expansion. This takes a long time to prove. By the way, this is also called the mean curvature, in case I didn't say, and it's precisely, rigorously defined as the divergence of the vector field, the outgoing vector field on the surface. That's how the expansion is really defined. But it's equivalent to, like physically speaking, it's equal to this. But it's really the divergence of a vector field. Okay, so the geometry equations, together with Einstein's equations, imply this after a bit of work. The rate of change of the expansion is related to the curvature, with the curvature is related to the stress energy momentum tensor in this way. And we assume there's some reasonable conditions, physically reasonable conditions that gets us to assume that this is less than or equal to 0. This is called the null energy condition. And then we see that this is less than or equal to 0. So the rate of change of the expansion is less than or equal to 0 always. So in a sense, it can stay the same. So the null expansion stays the same or decreases. It cannot bounce back upward. Physically, if at a point it's negative, it becomes even more negative. It keeps decreasing. So keep that in mind. Now we are ready to define what we call a trapped surface. If we have a space-time and you take a surface, we say the surface is trapped if both its expansions, the outgoing and ingoing expansions, are negative on S. We call it an apparent horizon if theta plus is positive and theta negative and theta minus is negative. Remember again that the normal thing that would normally happen without any black holes would be that theta plus is positive and theta minus is negative. That's what happens in flat space. But we say that the surface is trapped if both expansions are negative, and we can think of this physically as the light rays from the surface, whether they're outgoing or ingoing, they're both converging. And if they are converging and they continue converging, because the rate of change is negative, so it will continue converging, it will eventually end up in what we call a singularity. Singularity. That's how we define a trapped surface. And this is the main tool that we will use to define a black hole rigorously. So well, actually, at some point, you will see soon. So before we define a black hole, we will define something very important. To take a space-time, take any future-directed null curve, so that's the path that light will take, and take its, in a sense, limit point. Where does it go at infinity? Take that as a point. So I plus, this is vaguely speaking for now, I'm not defining it precisely. I plus consists of, in a sense, all the limit points of future directed null geodesics or null curves even, which reach arbitrary large spatial distances. This can be made rigorous by something in topology called compactification. There's a way to compactify the space-time, so add infinity points so that the space-time becomes compact. Normally it's not, it's R4, let's say, so it's not necessarily compact, but you can compactify by adding infinity points, and these are in the infinity points. These are the future null infinity. There's also future time-like infinity. There's also a future, there's also a space-like infinity, and there's also a past null infinity, and there's also a past time-like infinity. But we're not going to care too much about this yet. Let's just understand that via some notion of compactification, in which the geometry or the metric extends uniquely to that compactification, to those infinity points. So with respect to some notion of compactification, we have a notion of I plus all the limit points of future directed null geodesics. Then how do we define a black hole? A black hole is a region. If you have a space-time, the black hole is precisely this region. It's the past of future null infinity. So take any point in null infinity and take its past, and take all points in M that you don't find there. This is the black hole region. Physically speaking, these are points or events in space-time that do not have any null curves connecting them to infinity. So they are kind of, separated from infinity, from future null infinity. Physically speaking, you can think of future null infinity as a very distant observer, someone very far away that is measuring signals coming from everywhere. This person will not find any signal inside the black hole, because any point inside the black hole is in the complement of this. So the black hole region is the complement of this. So it's something that a distant observer will not find. And that is how a black hole is rigorously defined in general relativity. And a specific example is Schwarzschild solution. And indeed, you can show that the Schwarzschild solution satisfies this definition. The R less than 2M region indeed satisfies this definition. Okay. There are two important theorems in general relativity. The first one is a collection of theorems called singularity theorems. There's the Hawking singularity theorems by Stephen Hawking, and there's also the Penrose singularity theorem. They approximately say the same thing. They say that if you have a space-time that contains a trapped surface, then there must exist a singularity in that space-time. And the idea the idea is not too difficult. If you have, just to remind you, if you have a trapped surface, then all null rays are in a sense converging. And if you compute the limit of this of these curves, you will get something called a singularity. Vaguely speaking, a singularity is like a point in which something weird happens, like the curvature blows up, or the metric is not defined, or something like this. I'm being very vague right now, but the singularity theorem tells you that if you have a trapped surface, then you have a singularity. The second important theorem in general relativity, which is actually not yet a theorem, it's just a conjecture. It's called the cosmic censorship conjecture. It is not yet a theorem. It's not yet proven. There has been a lot of progress in the last many years, but it's still open. And it says that if you have a spacetime that has a singularity, then that singularity must live in a black hole, i.e. there are no naked singularities. A naked singularity is a spacetime with a singularity in which any point near that singularity is actually connected to I plus. So it is inside here. But the cosmic censorship conjecture says that this will not happen. It says that if you have a singularity, that singularity must be inside a black hole. So it must be in a region in which the events in that region are not connected to I plus. Of course, you can find spacetimes in which they have naked singularities, but somehow they're not going to satisfy Einstein's equations. So these are all properties of solutions to Einstein's equations. We're trying to understand properties of solutions to Einstein's equations. This is still a conjecture. So if we accept it for now, we can say that if we find a trapped surface, then we're done. We have found a black hole. These two theorems really simplify our search of a condition that promises the formation of a black hole. Just find a trapped surface. If you have an initial data slice, if you have a time slice of a space-time, find a trapped surface in that. If you find a trapped surface, then there will be a black hole. So it's a great progress in understanding black hole formation. Okay. Now, the hoop conjecture under spherical symmetry is indeed resolved, and I want to give you a sketch. First, can I hear from the organizers how much time do I have left? Because I don't want to go over time. I don't know when we
Uh,
start.
Now that's okay. We started a bit late, so you can finish on your time. So
Okay, thank you. Okay,
yeah,
maybe like five minutes more or
yeah,
so.
yeah. That's great. Thank
Thank you for your attention. I feel like I've been talking for 10 years, so I appreciate
you. No,
it. Thank you for staying with me. And if you're not staying with me, that's also okay. Okay, so now I want to talk about the a result that has been established. Unfortunately, not the hoop conjecture in general, but under spherical symmetry, and that has been established. And I want to give you a bit of the proof. Uh, so if you have a space time, take a sigma, a space-like hypersurface, which just means like a time slice in the space time. Fix a particle around two sphere. Before we even talk about Hooke's conjecture, we first let's define what spherical symmetry means. Spherical symmetry uh, uh, vaguely speaking, means that you can write in some coordinates, you can write the space-time metric in this form, where f1 is a function that depends only on t and r, and f2 is a function depends also on t and r. So nothing is depending on. So the functions that depend only on the radius away from a particular point, and r squared gamma s2 is just the metric on the round sphere of radius r. If you have done some, Riemannian geometry, you recognize this. If not, you can just follow from a distance. That's okay. Okay, so vaguely speaking, vaguely speaking, that's how we define spherical symmetry. Of course, it can be more rigorously defined using actions of groups on manifolds and so on, but we won't go there. So before we go into Hooke's conjecture, we need to first define what circumference means and what mass means. Luckily, under spherical symmetry, these are very easy to define. So the radius, so we can define the radius of the sphere by the equation. So the area of the sphere we can compute. And we can define the radius of the sphere via this equation. The area of the sphere is equal to 4 pi r squared. The area of the sphere is this double integral that we defined later on. It's something that depends on if you have the geometry, you can compute the area of the sphere. And the radiuses can be defined this way. Then the circumference can simply be defined this way. This becomes completely useless outside spherical symmetry, by the way, for reasons that you might see later. So that's how we're going to define the circumference. The circumference is going to be defined as 2 pi r, where r is defined this way. So that will be the length of the hoop that we will be passing through matter. The second thing we need to define is the mass. What definition of mass is there? So this has been an open question for a long time. There has been many definitions of mass that have been proposed. But luckily, under spherical symmetry, many of the proposed definitions of mass actually just agree, and you get an accepted notion of definition of mass of a particular surface in a spherically symmetric spacetime. So that's called we're going to call this the Brown-York mass. And it's defined like this. We have the surface, it's 1 over 8 pi, and you're integrating over the surface k0 minus k. K is the mean curvature of S. Again, that is just the divergence of the unit normal vector field. And K0 is the mean curvature of the isometric embedding of the sphere into R3. So this is going to be a bit abstract, but the definition of this mass is a bit abstract, but it does work. So first, what do I mean by this isometric embedding? So we can take the sphere, so let's say this is the sphere, take its induced geometry. So we just get the sphere with its induced geometry. There are theorems that tell you that under some conditions, you can always find this sphere with this geometry inside flat Euclidean R3. They're called the embedding theorems, or isometric embedding theorems. So under some conditions, and the condition actually is just that the sphere needs to be of positive scalar curvature. If the sphere is of positive curvature, then it can be embedded in R3. And when you embed it in R3, you can compute its mean curvature as it lives in R3. So the mean curvature is something that is not intrinsic to the surface. It's extrinsic. The mean curvature is something that depends on how the surface curves in the space it lives in. But the induced geometry is something that is just intrinsic. So you can take the induced geometry and embed it in flat R3 and then ask via this embedding, what is the mean curvature? And those will generally be two different things. In fact, there are theorems that tells you that those are equal if and only if the spacetime is already Euclidean. But either way, there are also theorems that tells you that this is always bigger than the mean curvature of the isometric embedding into R3 is always bigger than or equal to the integral of the mean curvature in a general geometry. There is also theorems that say this, and something related to isoperimetric inequalities. We won't talk too much about that. But either way, the mass is defined this way. And now we are ready to state the theorem. By those people in 2009, so not that long ago, like 16 years ago or so. Let M be a spherically symmetric, asymptotically flat spacetime with a regular center. I'm going to be very vague for now, and no past singularity. That just rules out something weird that we don't accept as scientists. It's called a white hole. It's when the expansion theta plus and theta minus are both positive. It's like the opposite of a trapped surface. It's the opposite of a black hole. And it's defined as the future of past null infinity. Like the complement of the future of past null infinity is defined in a certain way. And for reasonable reasons, we reject the existence of white holes. And so we make this assumption that there are no white holes, whatever that means for now. And if you have S around two sphere contained in a spherical space-like slice, then if the circumference is smaller than 2 pi times the Brown-York mass, then S is trapped, i.e. there will be a black hole. If the circumference is bigger than 2 pi times the Brown-York mass, then S is not trapped and there is no black hole. And so the Hooke conjecture, that's resolving the Hooke conjecture. The Hooke conjecture under spherical symmetry. Again, remember from the singularity theorem and the cosmic censorship conjecture, if you get a trapped surface, then you know that there will exist a black hole. Of course, a big part of resolving this conjecture is making the definitions of the circumference and making the definitions of the mass. So again, this is still an open problem in general spacetimes. Even under other assumptions, it's still open. It's only resolved under spherical symmetry, which is a very strong assumption. Okay, maybe the rest was just a sketch of the proof, which maybe I can skip because I've been talking for a long time. So I will stop here, and I can take questions if you have.
Thank you very much, Ahmed, for that excellent talk. Yeah, so the floor is now open to questions, and maybe there is one question.